Hiya, today I'm going to be solving the CIE AS Chemistry, October-November 2025, paper 33. The quantitative analysis bit asks us to read through the whole method before starting any practical work and to prepare tables where appropriate for our results and to show the precision of the apparatus used in the data we record. This is really just referring to the decimal places or the use of significant figures. Show your working and appropriate significant figures in the final answer to each step of your calculations. So it says here, the thiosulfate ion with the following formula decomposes when an acid is added. So they've used hydrogen ions in this equation to denote the acid donating protons, basically. The rate of this reaction can be investigated by measuring how long it takes for the solid sulfur forming to obscure the print on the insert. So sulfur, as you can see, the solid, is a product. By obscure, they mean to block the text. And then it says you investigate how the concentration of thiosulfate ion affects the rate of the reaction. So we are comparing concentration and rate. To measure the rate, we're seeing how long it takes the solid sulfur to block the text. The more the solid accumulates, the more of the text will be covered. It also gives us a little note down here that states, a small amount of sulfur dioxide, one of the products, may be formed in the experiment. It's very important that you avoid inhaling any fumes, and as soon as each experiment is complete, to add the reaction mixture to the quenching bath and rinse the beaker thoroughly. The reason for this being because the quenching bath will cool and dilute the mixture so no more SO2 forms. And by rinsing the beaker, we remove the leftover thiosulfate or acids. If the residues stay, they can keep reacting and release more gas. So our method includes two experiments, experiment 1 and experiment 2. Start off with experiment 1, we are asked to fill a burette with Fa1. Fa1 being 0.1 moles per decimeters cubed of sodium thiosulfate. That goes into our burette. It then says to run 40 centimeters cubed of Fa1 into the 100 centimeter cubed beaker. So this right here is our beaker, and 40 centimeters cubed of it will be filled with our sodium thiosulfate. Then it says to use the 25 centimeter measuring cylinder to measure 10 centimeters of Fa2. Our Fa2 being our acid, our hydrochloric acid, and 2 moles per decimeters cubed of that. So this right here is our HCl. It then says to add Fa2 to Fa1 in the beaker and start the timing immediately. So once we've added, we immediately start our timer. And then it says to stir the mixture once and place the beaker on the printed insert. This right here is our insert with our print. View the printing on the insert from above through the solution. This is meant to be an eye, and we're meant to view it from above. Stop the timing when the print becomes obscured or otherwise blocked. And then record this reaction time to the nearest second in the space for results. Empty the contents of the beaker into the quenching bath, we explained why earlier, and then rinse and dry the beaker so it is ready to use in experiment 2. And in experiment 2, it asks us to refill the burette with Fa1, our sodium thiosulfate, then fill the second burette with distilled water. So you wouldn't use the same burette, you'd use the second one to add H2O or distilled water. It says to first run 20 centimeters cubed of Fa1 into the 100 centimeter beaker, using, of course, our first burette that had Fa1. Then it says to run 20 centimeters cubed of distilled water into this same beaker. So another 20 centimeters cubed, but this time of H2O. It then says to use the 25 centimeter cube measuring cylinder to measure 10 centimeters of Fa2, our acid, same volume used in experiment 1. And then it says to add Fa2 to Fa1, like we did the first time. Start the timing immediately, and then stir the mixture once. Place the beaker onto the printed insert once again. And then to view the printing on the insert from above, once again. And to stop the timing when the print on the insert becomes obscured or blocked, record this reaction time to the nearest second in the space for results. Empty the contents of the beaker into the quenching bath, rinse and dry the beaker so it is used or ready to use in the next experiment. So really all that we have done here is we have diluted the solution. We have maintained an overall volume of 40 centimeters cubed. However, we have diluted our solution of sodium thiosulfate using our water in the second experiment. So really experiment 1 uses a more concentrated sodium thiosulfate. Everything else remains the same because the variable we are trying to measure is our concentration of sodium thiosulfate to test the rate, of course, using our reaction time. Now it says here that experiments 3 to 5 should just be 3 further experiments to investigate how using different volumes of Fa1 affect the reaction time. So really you would just use varying volumes of distilled water and sodium thiosulfate. It says here that the combined volumes of Fa1 and distilled water must always be 40 centimeters cubed because we are only measuring concentration and not volume, or how volume affects reaction time. It also says to not use a volume of Fa1 that is less than 15 centimeters cubed. This is because you would probably have a really long reaction time. The reason for this being is it's so dilute that it will take ages for the reaction or for the products to form in amounts that would obscure the print completely. So here it says to record all your results in a table. You should include the volume of Fa1, the volume of distilled water, the reaction time, and the reaction rate for each of your 5 experiments. These here are 4 features, meaning we will require 4 columns. The rate of reaction can be calculated using this formula right here. Okay, so here I've just drawn out our table with our 4 columns. Our first mark for our results would be our correct columns, our correct names for our columns. So the volume of Fa1, the volume of water, the time or the reaction time, and the rate. Our second marking point would be to use the correct units. Don't ever forget to use the correct units in your table or to even put the units in. For the volumes, it makes the most sense to use centimeters cubed. For time, they did say to use it to the nearest second, so that is an indicator that we'd be using seconds. And for the rate, it would be at seconds to the power -1. Really all that means is it is just the same as 1 over s because we're doing 1 over time and our time is in seconds. Okay, so now I have generated a table with results that should correspond to what is expected in an actual experiment. The third marking point here is to have recorded all the times to the nearest second, so we should be having whole numbers. This was mentioned in our experiments. They asked of us to round to the nearest second. There also, to gain this third mark, you must have also had volumes of Fa1 be given to both 2 decimal places and to end in 0 or 5. Okay, so the reason for this being, we had to have volumes greater than 15 but less than 40. Now, all of our values had to be no closer to each other than 5 centimeters cubed. And this would actually be our 4th marking point. So none of our values have to be closer to each other than 5 centimeters cubed because then there would be little difference. And at the same time, our volumes needed to add up to 40 centimeters cubed each time. So that would be for the 4th mark. So the 3rd mark was for them being to 2 decimal places. The reason for that being they provided volumes to 2 decimal places in our experiments, and for them to be to 2 decimal places ending in either 0 or 5. 0 or 5, again, like I said, is technically part of marking point 4. Our fifth marking point is for calculating the rates of all the experiments and for them to be from 2 to 4 significant figures. I went with 2 just to make life easier. It says our sixth marking point is if all times recorded increase with decreasing volume of FA1. So as the FA1 decreases, our reaction time increases. And this makes sense because the more dilute a solution is, the longer the reaction will take to fully finish. So the more time the reaction will spend making products. Marking point number 7 is really just comparing your results to the supervisor's results. So if you are within close proximity, so within the range 1.8 to 2.3, then you get the 7th marking point. And if you are within the range 1.9 to 2.2, a tighter range really, you get the 8th marking point. Now it's asking us to plot a graph on figure 1.1. The y-axis being the rate, the x-axis being the volume of FA1. Each axis must start at 0, 0, the origin, and we must ring any anomalous points and draw a line of best fit. So I've just rewritten the data for FA1 volume and rate to be able to look back at. So it's said to start at origin 0, 0, and we need to find appropriate scales for each axis. Down here we'd write, we'd write volume of FA1 in, of course, centimeters cubed. Up here I've already written rate and its units. Now in terms of scales, the most common scales really are scales that go up in 2s, in 5s, in 10s, and it really just depends on how big the numbers are and how big our graph is. But just by looking at this, looking at the axes, I feel like 5s would be most appropriate because we need to fill them as much as we can of the graph. We also need to would love to have a more accurate graph, so we avoid bigger scales. We'd avoid 10s because we wouldn't really be as accurate when it comes to our 35s, our 25s, and we avoid 2s scales because we're probably not going to end up getting to 40 by the time we reach the end of the axis. So let's do that. So we have 5, 10, 15, 20, 25, 30, 35, 40. Perfect. And on here we would have, we could have the same as well. 5, 10, 15, 20, 30, 25, 30, 35, 40, 45, 50. Okay? Now we just have to plot these coordinates essentially. So we have 40 and 42, which would be up here. Up here. Then we have 35 and 36, which would be around here. Because we went up in 5s, each little box means 0.5. And we have 30 and 29 up here. Then we have 25 and 22 around there, and 20 and 17, which is around here. Okay, there you go. Now, as you can see, there seems to be a straight line trend, and there doesn't seem to be any anomalous points, but if there was one here, for example, we just ring it and not include it in our line of best fit. So since it looks like it's going to be a line, I'm just going to draw a line that passes from this point to this point. Oh, that doesn't seem quite right. Sorry, 1 second. Try and get it as accurate as I can. Now, the line does not have to go through all the points. It's a line of best fit after all. It just has to go through the majority of points, okay? So, there you have it. What are our 3 marking points for? So, our first mark is for using the correct units and names for the axes. Marking point number 2 is for correctly plotted points. And then mark number 3 is for a good line of best fit, whether it be a straight line or a smooth curve that ignores any anomalous results identified by the candidate. It then asks us to use our graph to determine the time it would take for the print to be obscured if 7.5 centimeters cubed of FA1 are used, and 32.5 centimeters cubed of water, and 10 centimeters cubed of FA2. Show clearly on the graph how you've worked out your answer. So really all we care about is the volume of FA1, and what we're going to do is we're going to work backwards. We're going to go to our 7.75 centimeter cubed volume, and then work our way backwards. So really, this line should be extended so that it should be around this much. And then we go to 7.5 centimeters cubed. That would be around, yeah. And then just work our way backwards. That is around 0.5, 1.5, a rate of 1.5, but they did ask for the time. And really, time and rate are inversely proportional. So what we would do, if rate is equal to 1,000 over time, then time would also be equal to rate divided 1,000. So it would be 1.5. Sorry, I don't know if I said that right. What I mean is time equals 1,000 divide rate. So 1,000 divide 1.5, which is equivalent to 667 seconds. You get 1 mark for a correctly drawn line and a rate that correctly reads within half a small square, as well as carrying out the calculation and then giving an answer within 2 to 4 significant figures. It then says that a student carries out the same method as given in A, but uses a different concentration, and the student's calculated values for the rate are plotted in the graph below. State whether the student's results show that rate is directly proportional to volume of FA1 used. Explain your answers. Well, really, as you can see here, if we were to draw a line of best fit, for this student's graph, what we would find is that really it's around here, and it does not pass through the origin, 0, 0. When a graph passes through the origin and it's a straight line, it shows a directly proportional relationship between our x-axis and our y-axis. However, this is not the case. So our first point for our first mark would be that the correct line of best fit, so our mention of best fit is our first mark. 2 shows, does not pass through the origin, or 0, 0, thus not directly proportional. Now, if you thought that the line of best fit does not look like mine and does actually pass through the origin, so like let's say the line of best fit was actually like this. Oh, see, I'm not good with lines, but yeah. Then in your case, you could write the correct line of best fit. Passes through 0, 0, therefore it is directly proportional. You have those two options, but I say that it doesn't. Now on to the next experiment. When hydrated sodium thiosulfate is dissolved in water, the temperature of the liquid changes. We'll carry out an experiment to determine the enthalpy change when 1 mole of hydrated sodium thiosulfate dissolves in water. Our Fa3 is our hydrated sodium thiosulfate. The method is as follows. Support the cup in the 250 centimeter cubed beaker. Use the 50 centimeter cube measuring cylinder to transfer 30 centimeters cubed of distilled water. Then measure the temperature of the water in the cup. Record this in the space for results. Weigh the container with Fa3 and record the mass. Then tip all of Fa3 into the cup. Stir the mixture until the minimum temperature is obtained. Then record this temperature. Weigh the container with any residual Fa3. So again, record the mass. Calculate and record the mass of Fa3 added. So basically, once you first added your Fa3, then you weighed the residual plus the container. When you subtract these masses, you end up with how much you had actually transferred. Then it says calculate and record the temperature change. So it says results here, so we're meant to generate a table basically. We need to look out for the keywords such as record to find how many columns we would need for our table. So record is mentioned here, 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 and here. That makes 6 columns that we must generate. Okay, so I've added all 6 columns. Now the first mark would be for all the 6 columns being the correct names, the correct units, so grams or degrees Celsius. Our second mark here would be for all 4 balance / thermometer readings being shown. Both are thermometer readings, so these two, ending in 0.0 or 0.5. This is just because the thermometer scale doesn't allow more accuracy than that. And then both weightings, so these two, to be either to 2 decimal places or 3, depending on your scale, but they have to both to be to the same decimal places. So however accurate your scale is, you must use the number of decimal places present on that scale. Our third mark would be for correct calculations, so correct subtractions basically here and here. And then our last mark, our fourth mark, would be for our change in temperature to be within 1 degree Celsius of the expected temperature change for the mass used. It then asks us to calculate the number of moles of hydrated sodium thiosulfate added. So really, this is the formula for hydrated sodium thiosulfate, and this is the MR. It's really just all the individual atomic masses found on the periodic table added up, and the mass we obtained or we transferred of Fa3 in our experiment was 6.5 grams. So as you know, the number of moles is equal to the mass divided by the MR. So to find the number of moles, we just do our 6.5 divided by our 248.2, which would give us 0.026 moles to the nearest 2 significant figures. 2 to 4 significant figures is accepted. Then it asks us to calculate the energy change in J in your experiment. Now, our energy change, in J, I meant in joules, right, is equal to the mass times the heat capacity times our change in temperature. So the mass is referring to the volume of water heated. So we consider 1 gram to be equivalent to 1 centimeter cubed. And our specific heat capacity is 4.18. It's fixed. Our temperature change in this experiment was 3.5. So we're just going to do we're just going to multiply these three. So 30 times 4.18 times 3.5. And we will end up with 438.9, or 439 to the nearest 3 significant figures. Again, 2 to 4 significant figures is completely accepted. It then says to calculate the enthalpy change in kilojoules per mole when 1 mole of hydrated sodium thiosulfate dissolves in water. Now, we have, okay, so our enthalpy change is equal to our energy change divided by the number of moles. So really, our energy change, which was 439, divided by our number of moles, which were 0.026, will give us 16,880 for significant figures. Oh, sorry, right. Oh, I was about to make joules per mole. Because our energy change was in joules, to make it into kilojoules, we need to divide by 1,000. So we really have 16.88 kilojoules per mole. And it's asking us for a sign. Now, this should actually be a plus sign. Why is that? That is because when we had a hydrated solid into water, this is an endothermic reaction. And for this very reason, we had a temperature change, a negative temperature change. Our temperature actually decreased because heat was absorbed from the surroundings, from the water. So the water actually gets colder and the final temperature is lower. Okay, then it says that the value previously calculated can be used to determine the enthalpy change of when we add anhydrous sodium thiosulfate to water to form hydrated sodium thiosulfate. It's asking us to outline the method of one further experiment we could carry out to find this new enthalpy change. Show how we would use our previous results to calculate this one. Okay, so our first mark would be obviously to repeat the experiment, except with sodium thiosulfate this time. Marking that point number 2 is to use the same, not necessarily same, but a known volume of water. Our third mark would be to use Hess's law. The reason for this being is we can't measure the temperature change directly, because when we dissolve an anhydrous solid, the process would be too fast to get an accurate measure of the temperature. Now, using the Hess cycle, what we would do to get our enthalpy change is we'd subtract our enthalpy change by our previous calculation. Why this is because, as you can see, according to the Hess cycle, we should go in this direction. Now, to go from our solid to our aqueous, what this is dissolution. And then here, going from aqueous to our hydrated salt is, of course, hydration. Since this arrow is going against the direction we are meant to be headed in, it turns negative, or in other words, we're subtracting. So we subtract this enthalpy change from this, which is our BIII, 3 I's, to find our delta HR. For qualitative analysis, it says that each test should be recorded with the observations in the spaces provided. Any color changes seen should be noted, any precipitates formed and their solubilities when in excess of reagents, the formation of any gases, and if a gas is formed, any further tests that could possibly identify it. You should clearly record at which state a test, an observation is made in a test. And if there isn't, you should just write no change. You could provide alternatives like it remains the same, but just go with no change because it makes life a lot more easier. Where reagents are selected for use in a test, the name or correct formula should be given for the compound. If any solution is warmed, a boiling tube must be used, and if a solid is heated, a hard glass test tube must be used. Rinse and reuse test tubes and boiling tubes where possible. No additional tests should be attempted, and the practical is as follows. They want you to half fill a 250 centimeter cubed beaker with water, so right at the 125 centimeter cube mark. Place it on a tripod and a gauze. Heat the water with, I'm assuming, a Bunsen burner until boiling. Then you switch it off. Then it says this will be your hot water bath for the use in BI. Start AI while the water is heating. So it says Fa4 is an aqueous solution and it contains 3 whole ions. 1 ion is not listed in the qualitative analysis notes. Fa5 is an aqueous solution containing 2 ions. The cation in Fa5 is in the notes. The anions Fa4 and Fa5 in both Fa4 and Fa5 contain sulfur. Carry out the following tests at a 1 centimeter depth of either Fa4 or Fa5 in a test tube and record your observations. So really I've just noted down all the mark scheme answers because I don't have Fa4 or 5 in front of me and I would not be able to conduct them otherwise. However, it does ask us to use our observations to deduce the identities of the ions present in Fa4 and Fa5, to give the formula of each in the table, and if we're unable to identify an ion, to just write unknown. Okay, so in regards to just note-taking or like writing down observations, like we said at the very beginning, write down any color changes. If there's fizzing, then write further tests to confirm these gases. Solubility matters. If there's excess, is it still soluble? Is it still insoluble, or does it dissolve? And just try to write down as much as you can, because if you lose points or miss bits somewhere, you can gain them somewhere else. And so just to move on to the question, we need to identify the ions in Fa4 and Fa5. So they said there are 3 ions in Fa4 and 2 in Fa5, and both anions contain sulfur. So if we take Fa4, when we added aqueous sodium hydroxide, we got a red-brown precipitate. We also got it with the aqueous ammonia. This is the test used to indicate the presence of Fe3 plus ions, so we know we have that for sure. Then further down the line, when we add aqueous barium chloride followed by barium nitrate, the known test for testing the presence of SO42 minus ions, we get white precipitate, for it makes barium sulfate. So we know they're SO42 minus ions. We also have the same result here for Fa5, so they must also contain SO42 minus ions, and these ions contain the atom sulfur. So we know that this is probably the correct answer, and I can confirm that it is. Another ion, and the ion that they said isn't in the table because Fe3 plus and SO42 minus are both in the table at the very end, we can tell is present is the H plus ion. This is due to the fizzing that occurs with the sodium carbonate. Sodium carbonate is a base. It reacts with acids which donate hydrogen ions, and so that is our third ion. When it comes to Fa5, we have white precipitates forming with our sodium hydroxide, except this time they're soluble, unlike the red-brown precipitate. And that is the distinguishing point. Besides the fact that the precipitates are different colors, Al3 plus actually is soluble in excess, while Fe3 plus is not. The precipitate formed from it, is not. So there we have it. Then it says that both Fa6 and Fa7 are either propan-1-ol or 2-ol, or methanoic acid or ethanoic acid. You will carry out tests to investigate these. Each test uses 1 centimeter depth of each solution. Record your observations. I've recorded the answers. And then it says to use these observations to deduce the identities. I've drawn out the molecules here on the side, just because. So it's asking us what Fa6 is. First thing I see is right here, adding aqueous sodium carbonate has resulted in fizzing, so it is definitely a acid. Is it ethanoic or is it methanoic? Well, if we look at test 1, it turns paler pink, so it does react with acidified aqueous potassium manganate. Only methanoic acid would do this. Methanoic acid is a reducing agent, and it would react with our potassium manganate. However, for ethanoic acid, there is no hydrogen bond, bonded to our carbonyl carbon, as you can see here, and therefore it would not react with our potassium manganate. So it cannot be oxidized further under normal conditions. Now, so what we're going to say is Fa6 is methanoic acid. And I can say 1 because it reacts with sodium carbonate. 2, and this is necessary. We need to mention both points for us to get the full mark, because both ethanoic and methanoic acid would react with sodium carbonate. So we can say reacts with potassium manganate. Then it says, what is Fa7's identity? So the thing that stands out to me here is test number 2. It says we add 2 centimeters depth of aqueous iodine followed by drops of aqueous sodium hydroxide until the color just disappears. What kind of test is this? This is our typical iodoform test. So our propan 2-ol would give a precipitate in this case. However, our propan 1-ol would not, and that is how we would distinguish between the two compounds. So our Fa7 is propan 2-ol. And the answer is, or the reason is, because it gives positive result with the iodoform test. Because if you take a look here, our propan 2-ol, it has a carbon attached to both a CH3 and an OH at the same time. However, here we do not have a carbon that is attached to a CH3 and an OH. We have a carbon attached to 2 hydrogens and another carbon atom. Lastly, it states that a student carrying out a similar set of tests identifies 2 unknown compounds to be ethanol and propanoic acid. Write an equation for the reaction between these two. Ethanol is as follows, propanoic acid is as follows. When they react together, they form ethanol propanoate, an ester plus water. So we just need to write their formulas in a condensed form. So we have our ethanol, our CH3, CH2, OH, plus our propanoic acid, our CH3, CH2, COOH, to give our ester, which would look like this. It would look like this. Dun, dun, dun. C, and these lines represent hydrogen atoms bonded at the ends, but I'm too lazy to draw that out, so there's that. It just looks CH3, CH2, COO, CH2, CH3, this being the COO ester link plus a water molecule, because as you can see, a hydrogen has been knocked off here, and our OH has been knocked off here, so we end up with 2 hydrogens and an oxygen to form our water, and that is it.